Today, we're building memory. Last episode, we built a calculator. And worked. But the moment the inputs changed, the answer disappeared. Every result was temporary. It needed a way to hold on to information. So now, it's time the calculator can remember. But first, we need to change the user panel. I have to give credit to Tun Rae here. She was the one who showed me that memory was possible. Definitely check out her channel if you haven't already. With the redesign panel complete, we can now see inputs and outputs more clearly. And we have an interface for memory selection, memory write, and memory reset. Now it's time to design the memory selection circuit. Two switches form a 2-bit addressing system. And with it, we can create 4 unique combinations: 00, 01, 10, and 11. Enough to uniquely select between live output and 3 separate memory banks. I will use inverters, AND gates, and color coding to create the 4 combinations and build a path for each address. As you can see, routing all the required signals into the AND gates becomes a bit of a puzzle. Alright, that's the addressing finished. Now we need to rework the output system, so live output only shows up when 00 is selected. Let me show you that the live output selection is working. When I select anything other than 00, the output goes blank. And since we don't have any memory yet, there's no other output to display. To keep the calculator and the memory circuitry visually separated, I add a divider frame. Right now, I'm creating the circuits that will feed into the future memory banks. And I'm also updating some of the color coding to make the purpose of the circuits more visually intuitive. At this point, we finished all the necessary preparations. So now I can finally start working on the memory itself. But before I can build the memory banks, I first need some kind of memory cell. And Reforj actually allows us to build a so-called D-Latch. It's basically a combination of receivers, emitters, and a pair of inverter gates. And why we need the inverters will become clear later. But the important part is the reflector. Because that's what latches the signal into a loop. Even after the original input disappears. And that's memory. Now we can finally build the first memory bank. First, I'm setting up an AND gate system. And this checks two things. Is this memory bank selected? And is write enabled? Only when both are true, the incoming signals are passed on to the memory cells. Now I start building the initial version of the memory cells for the first memory bank. Later on, I'll revise them slightly to support resetting. You might notice that I'm now placing an OR gate before the inverters. Because the circuit is already emitting a signal, this becomes a cleaner way to combine the input with the feedback loop. I think I actually want some spacing to see the current state of the memory cell. Let's try writing something to the cells. Success! We can see that the memory bank is now storing the signals. Let's create the output. To determine whether the output should actually be transmitted, we need another AND gate system. This one takes the signal from the memory cells and checks whether the memory bank is currently selected. I slightly rework the output selection system so I can easily switch between the live output and the memory banks. And then I start making the adjustments needed to allow the memory to be reset. Green is write enable. And red is reset. So now I actually have to move everything one block backwards, because I need to fit an OR gate between the two inverters. And this is also why I needed the inverters in the first place. If the reset signal passes through the OR gate in state 1, the inverter turns it into state 0, effectively breaking the loop if one existed in the cell. So essentially, this wipes the memory clean. And once again, we need an AND gate system to check two conditions: whether the memory bank is selected and whether the reset switch is enabled. So let's write the calculator's result to the memory. We can see the signal appearing on the display, though it is a bit difficult to read near the outer edge. To improve the contrast, I make the size black as well. That's much better. Now let's try resetting the memory. And there we go. The signals are cleared from the cells. Now that the first memory bank is working, the rest is mostly repetition. So I built the remaining memory cells, add some color coding to make the different memory banks easier to distinguish, and to finish things off, a bit of cleanup, lighting, and the final touches on the frame. Let me show you the calculator at work. I'll switch between the live output and the memory banks. Now let's clear one of the memory banks and save the result of the calculation there. And as you can see, the calculator can still recall that result even after we switched away from the memory bank where we stored it. And there we have it. The calculator can now store information, retrieve it later, and continue working even after we've switched away from the memory where it was stored. It's a small feature, but it opens the door to much more interesting behavior in the future. Thanks for watching, and I'll see you in the next one.